Hi everyone! Welcome to our ECCV 2020 oral presentation of LIMP, Learning Latent Shape Representations with Metric Preservation Priors. Proudly presented to you by Luca Cosmo, Antonio Norelli, Oshri Halimi, Kimmel, and Emanuele Rodolà. In this work, we present a novel variational encoder loss that promotes the preservation of metric properties of the reconstructed surface. But let's start with the basics. In the context of neural networks, a generator is a trainable function, returning a new element of a desired domain, such as 3D shapes. This function takes in input a latent code, representing the element in a low-dimensional vector. One widely used technique to construct a generator is through the training of an autoencoder, where the encoder function compresses the input data, while the decoder, or generator, reconstructs the input data from its compressed latent code. The idea of training generators, and in particular variational autoencoders, has already been applied to 3D deformable shapes and point clouds. One of the first attempts is the work of Latent et al., in which a simple variational autoencoder is trained on a large shape collection. They show the ability of the network to perform interpolations and generation of new shapes. More recently, Aumentado Armstrong et al. Trained a variational autoencoder on point clouds, using a spectral regularizer to obtain a better disentanglement of pose and style. Even if showing the potential of generative models on deformable 3D shapes, these methods share similar drawbacks. The reconstructed shapes look noisy and deformed, especially when reconstructing shapes far from the training set. Most importantly, they need huge datasets during training time to obtain reasonable results. On the other hand, geometric approaches are able to produce plausible and detailed reconstructions of interpolated shapes, but they usually require the manual modeling of elastic energies over the surface and costly optimizations. With our work, we try to merge the benefits of the two approaches, developing a learning framework able to efficiently interpolate and synthesize new shapes, sampling from a disentangled latent space. Moreover, thanks to our geometric priors, we require just a few training shapes to construct a well-behaved latent space, which reflects the geometric properties of the shape space. As previous works in 3D deformable shapes learning, we train a variational autoencoder, where we want to minimize the difference from the input and the reconstructed shapes. In particular, we want to obtain a well-behaved latent space that reflects the geometric properties of the reconstructed shapes, especially in terms of shape interpolation and disentanglement. To better explain our idea, consider the following example of a training set composed by just 11 shapes. Take the sitting cat X and the standing cat Y. We translate the preservation of the metric Z between these two quasi-isometries to the formation of a linear path in the underlying latent space. This has the effect of promoting naturally looking deformations, where all the interpolated shapes are synthesized by the generator from the interpolated latent code and have never been seen during training. We want to remark that we do not assume all the shapes of our dataset to be nearly isometric. We just assume that the interpolation between two shapes exhibits a bounded distortion. That is, given two shapes, their interpolation can be phrased as a sequence of near isometries, which minimize the total amount of metric distortion. This property of the latent space is obtained through a combination of three different loss terms: a standard reconstruction loss, which accounts for the reconstructed shape to be as close as possible to the training input shape, and two additional terms: an interpolation loss that penalizes the deviation of the reconstructed shape metric from the linear interpolation of the metric of the two original shapes, and a disentanglement term that promotes disentanglement of pose and style in the latent representation. Let's first consider our interpolation loss. Given two input shapes I and j, with corresponding vertex positions xi and xj, and associated latent codes zi and zj, we compute an L2 loss on the difference between the linearly interpolated metric of the two original shapes and the metric of the shape decoded from the interpolated latent codes. We make use of different metrics in our terms. In the reconstruction loss, we just aim to preserve the Euclidean pairwise distances. This leads to an accurate reconstruction on the training points, but a distorted reconstruction along the interpolated paths. The second metric that we minimize is the local Euclidean distance, accounting for a local rigidity of the shape. With this loss, we require that the interpolation on the latent space corresponds to an interpolation of the pairwise Euclidean distances in a local neighborhood of each point. Finally, we further improve the reconstruction result by also minimizing the geodesic metric distortion, inducing a better global behavior of the reconstructed shapes, where the metric is not only preserved locally, but also in a global scale. We show how an efficient backpropagation through the geodesic distances can be achieved by using the heat method for geodesic computations, which makes them fully differentiable with respect to the point positions. To induce disentanglement on the latent space, we also make use of a third loss term. We thus obtain a part of the latent code dedicated to encoding the style of the shapes, which is an intrinsic property, while the remaining part will encode just the extrinsic pose information. The main idea is that if we interpolate just the style part of two nearly isometric shapes, we do not expect any change in the resulting reconstructed shape. On the other hand, if we take two different subjects and thus non-isometric shapes, and interpolate only their pose-related latent code, we do not expect the shape to change appearance, and thus we expect the shape to preserve its geodesic metric. With this loss term, we can easily achieve disentanglement of pose and style in the latent representation, yielding a more expressive generative model. Note that we do not require the different subjects to have corresponding poses, since the disentanglement is entirely driven by the metric preservation prior. To conclude, we propose two metric-based loss terms, which act on the latent space of a variational autoencoder. In this way, we learn a generative model for 3D deformable shapes, with a latent space that reflects the interpolation and disentanglement properties of the output shape space. We show in our paper that our method is able to achieve better reconstructions of interpolated shapes than state-of-the-art works, especially when a small dataset is available for training. We also demonstrate how the latent space can be structured to obtain disentanglement between pose and style, without requiring any labeling of the poses of the input shapes. Our method is not only suitable for human bodies, but we successfully used it for various shape classes, like human faces and hands, animals, and in general, it can be applied to any deformable shape, which interpolation behavior exhibits bounded distortion, as for instance, in tissues and clothes deformations. We also prove in our experiments that the learned latent representation is amenable for a variety of different tasks and operations on the shapes, like arithmetic operations on pose and style, reconstruction from partial point clouds, and generation of unseen subjects in unseen poses. Thanks for your attention.